Assessment graphs. For the first question, traversals, here we can see the graph and we see what features apply to it. Is it undirected? No, you can see that there's arrows pointing, the edges are pointing to one another. So you can say that it's a directed graph. It's also not acyclic, but instead it's cyclic because here you can see it contains one cycle where A goes to D, goes to E, and goes back to A. So it contains at least one cycle. And then see if it's connected. If it's connected, we picture if this is undirected. If all the nodes are connected with each other, then it is connected. And you can see that if this is all undirected, it is connected. Every node here is connected with each other. And is it strongly connected? So for strongly connected, we just see if every node has a path to one another. You can see that E goes to B, but B doesn't go to E. So it is not strongly connected. For the next question, we do a depth first search starting from A, and we go alphabetically. So here, the neighbors of A, we can see is G, H, and D. We know that D is the lowest in the alphabet, so we'll go D first. So D is visited. And then since this is depth first search, we go in the node and we explore the node's neighbors. So here D has the neighbor of E, has one neighbor, E. So we next explore is E. So as you can see here, A, D, E. This is the ones we have visited so far. Next, we go in E and see its neighbors. We see that A has been visited, so we don't check A, and then we check B instead. So B will be visited. So this whole cycle of like going into D from A has ended. So now we visit the next neighbors of A, which here I'll just make a cutoff so it's much clearer. And then we go visit G, since G is lower than H in alphabets. So G, we visit, and it has no neighbors, as you can see. So that's done. Next, we visit H, which is the final neighbor of A. So we list that there, H. And then we see C or F. We see that C is lower in alphabet than F. So we visit C first, as you can see. And then we go in C, we see the neighbors, and C has only one neighbor, which is F. So we visit F. And then we go back to H, and we see that F has been visited. So when we go back again, and then we finish the whole depth first search. The next question is doing a breadth first search starting from A. Okay, as you can see here, if we start from A, we explore its neighbors first. We'll go, but this is breadth first search now. So we'll just do the first layer right here. So if we see here, we know that D is first. So D, add that to the list, G, and then H. But the next step we have to consider is the next layer, which you can see as these ones. This is the next layer. But take note that we visited D first. So wait here, I'm gonna just make this clear. We visited D first, so we have to check these neighbors first, actually. So we have to go E first. So we want to do E first. Then we visited, next was G. So G doesn't have any neighbors, so that's good. And then we want to see H, which has two neighbors, C and F. And since it's alphabetically, we do C first, and then we do F. So C, and then F. And then finally, the last level, which is just B, we just put that here. We just visit it, which is E's neighbors, because C and F doesn't have any more neighbors. Well, they don't have any more neighbors. For the next part of this assessment, counterexamples. For question 1, in an undirected graph, we can see that BFS and DFS actually can have the same order. What if they're all just like nodes that are connected by one edge? So you can see from S, A, B, C, D, they're all connected just by one. You can see that they both have the same order where they go S, A, B, C, D. So this disproves the statement. For question 2 here, the graph I drew disproves the statement because as you can see here, the minimum spanning tree, so S to C has to include the maximum edge rate, which is 4. Also from S to D, it also has to include the maximum weight edge because 4 to 2, 6 is less than this top one. So the minimum spanning tree does have to include the maximum weight edge. So therefore it disproves the statement. For question 3 here, I drew a graph which disproves the statement because as you can see here, there's 2 minimum spanning trees that are the same actually. Here from S to A, it's 3, but you can go from B to A, which is also 3. So there's 2 different minimum spanning trees at this case. So therefore, this disproves the statement, which states that there can only be 1, because there's 2 minimum spanning trees from source to A, which is therefore false. The statement is false. Thank you.